Ladies and gentlemen, welcome everyone. I am Dr. Roland A. Drolet, PhD in Biomedical Engineering from the University of Toronto, 1971. I am the developer and inventor of the RUMART PEM system that has helped over 1 million people all over the world who were suffering from all kinds of health problems. I'm going to just tell you a little bit about cosmology and astrophysics. Of course, there is a book that I've referred to earlier by Mr. Evans, and giving a good introduction in French. There are numerous books in English as well. So here I just want to make a small, a short link between general relativity and the Big Bang Theory, the evolution of our universe. Just to show you that in 4 dimensions, what we call the length element is not only the x, y, z regular space in 3 dimensions that we have here, x, y, z, usual representation of 3 dimensions, but we need a 4th dimension, which is the time. So the time is seen here as an element of distance. So because we are in space-time, so this is the element of space-time because it involves the 3-dimensional space and that of time, okay? So actually, I just want to show you that from vector theory and Pythagoras, I should say, theorem, you have dx in the x direction, dy in the y direction. So the length element from Pythagoras theorem is dx squared plus dy squared. If you are in 3 dimensions, you have to add the dy squared in the z dimension, I mean, dz squared. Now, the 4th dimension could be seen upward here, but the best way to visualize that is by representing the growth of the universe from the Big Bang, punctual Big Bang, say the size of an atom or even smaller, that grows very fast, and at some point we can say that the radius of the universe, spherical universe, is R1, then R2, it gets bigger and bigger, and you have an expansion there. And when the universe is said to be like a cold universe that is away from the basic Big Bang, then this is what we call the Robertson-Walker universe that grows like almost an ideal gas expanding and moving away from the Big Bang. But this happens all around the Big Bang, of course. But here we represent the spherical universe by its radius, and then the vertical line represents the time. This is the way that the universe expansion from the Big Bang is represented in most books talking about astrophysics and cosmology. So this is just general presentation about the application of the general Einstein's equation that we have shown earlier in earlier video clips. For a particle, we have his equation that we have seen, including the square of the energy of a particle, which is the square of mc squared. That makes m2c4 for the square of mc squared. Okay, this is the energy relative to the center of mass, but we also have an energy related to the momentum or the displacement or the motion of the center of mass multiplied by the speed of light, so square, it's p squared square. The terms here are defined on the right. W for energy, that's my preferred symbol. Einstein used E, but as far as I'm concerned, I use E for electrical field, so often I use W for energy, and it says work in English. The momentum, quantum mechanics, momentum is not only mass by velocity, but it's mass by velocity plus the charge multiplied by the potential vector. This is caused by the fact that when a particle hits another particle, it stops it, so it's like it induces a potential vector which creates the magnetic field perpendicular to the direction of motion. And this induction of magnetic field, or its potential vector creating it, is dependent on the charge of the particle. Okay? C is the velocity of light and m is the mass of the particle. So for what we call cold matter universe, or pressure is very low, then we call it the Robertson-Walker universe, and we have the equation that the density of energy multiplied by the cube of the radius of the universe is a constant. If you have, on the other hand, at the origin near the Big Bang, you have only ultra-relativistic gas, where the particles moving very fast. So then in these cases we have that the energy of the particle is really the momentum multiplied by the speed of light. Its energy as a function of mass becomes negligible compared to its momentum multiplied by the speed of light. So in these ultra-relativistic gases, we have that density of energy multiplied by the radius to the 4th power is equal to the constant, to a constant, okay? So here we just write that E of t is the density of energy, radius of universe that is expanding. So this here is just showing what happens when the universe is expanding. We have the actual radius of the spherical expanding universe given by the radius at the start multiplied by the exponential factor where e is the basis of natural logarithm 2.1828 and this is to the power of the Hubble constant multiplied by time. So Hubble constant is like a frequency here. So the universe per second, which is very low, but it's like the rate of creating and disappearing of universe, if you will. If we consider that universe would be created, expand, and then diminish again, just like an oscillator, we could say see the H0 as the oscillating frequency. And coming back to this expanding Robertson universe, we have the equation of ideal gas that could be applied, where the actual pressure will be the energy divided by the volume. So this will be like the same units of density of energy will be pressure. Okay? Now, just simply, if you want to go deeper into this, I invite you to look into the book Astrophysics from Evers. This is in French, but there are so many books in English that you can find on the net. Last point, I want just to mention that in our expanding universe, the frequency of any electromagnetic wave is actually reduced inversely proportional to the increased dimension of the universe. So this is of course in the long term, but it's important to know theoretically that the frequency of all electromagnetic wave in our universe are slowly reducing as the universe expands. This is why the initial electromagnetic wave emitted when the first electromagnetic wave were radiated from the early universe are down to the frequency of microwave, which is equivalent in energy if you place the term Boltzmann constant multiplied by temperature of the cosmic background, which is about 2.726 degrees Kelvin, then you get the energy of a microwave. Okay, so that's about it for the introduction of these not so simple subject, but I just wanted to give you general ideas so that you feel that you can understand the basics of this. Okay, so take care, and I wish you well for all the rest of your life.